Now that we have created our cool triangle shape functions, we can start playing with this function. I have here a right triangle drawn on graph paper. As you can see, it's printed graph paper because I ran out of actual graph paper and I'm too lazy to get more. Anyway, I'll make this side here, the hypotenuse, have a length of 1, just to make our lives simpler. And I'll call this angle here bow tie because bow ties are cool. Let's see if we can find the coordinate of this find all the coordinates of this triangle using our new functions. Just as a quick review, we have 3 functions: sine, cosine, and tangent. Taking an angle, not the right angle, but another angle in a right triangle, which we can call Bob, we can find the sine of Bob by finding the ratio of the opposite side, in this case 9, over the hypotenuse of 41. The cosine of Bob is the side next to Bob, the adjacent side of 40 over the hypotenuse of 41. Finally, the tangent of Bob is the opposite side of 9 over the adjacent side of 40. We can remember this by the mnemonic SOHCAHTOA, which stands for sine opposite hypotenuse, cosine adjacent hypotenuse, and tangent opposite adjacent. Now that we've reviewed our trigonometric or triangle-based functions, we can go back to our triangle on a grid. We have this point as the origin, 0, 0, and this side has a length of 1. Now we can try to find the coordinates so we know where our triangle is. Well, actually, one thing to consider if you want to pause here is, do we know yet what triangle this is going to be? Why or why not? Can we find the coordinates from this information? What if we don't have enough information to find out? Okay, I am going to start by assuming we do have enough information, but you can try to prove this if you want. It would probably be beneficial if you want to think about the law of sines and cosines later. Anyway, so assuming that we can find out all the coordinates of this triangle, we can call this point something, 0, because it is across something, but it's up 0. And that makes this point something, something else. Let's see if we can use our new functions to find out what something and something else are. We know that sine of bow tie is opposite over hypotenuse. And that means that since the hypotenuse is 1, this is just the opposite. So then the opposite side has the length of sine of bow tie. So something else must be sine of bow tie. Remember that sine outputs a number that's a ratio. When the ratio is over 1, it'll output a length. So this can make this length sine of bow tie. So then something else is sine of bow tie because something else is both the y coordinate of this point and the length of this side. Can you see why? Then we can move on to cosine. The cosine of bow tie is the adjacent side over the hypotenuse. Again, since the hypotenuse is 1, the output of the cosine function is the length of the adjacent side, which means it's just the length of the adjacent side, not a ratio, which means that something must be cosine of bow tie. Again, something is both the length of this side and the coordinate here and here. We have now found the coordinates of our triangles. That's pretty cool. If we know one side in a right triangle and one angle, we can find the coordinates of the rest of sides. And it makes sense. Our functions output ratio. So if you know one side in the ratio, you should be able to find the other. But we still haven't used our tangent function. Let's see what that gives us. Tangent is the opposite side over the adjacent side. In this case, this is the rise over the run, which would be the slope of the hypotenuse. That's interesting, but I can't think of anything else to do with it right now. So I'm just going to keep in mind that the tangent equals the slope and draw more triangles, because drawing triangles is fun. I think I may have gone a bit overboard in drawing triangles. Oops. It's pretty cool though, because now it looks like almost a part of a circle. Actually, circles are fun. I'm going to finish the circle. Wait a second. Now we have a way of defining sine and cosine for all angles. We said that the coordinate here is cosine bow tie, sine bow tie. So now we can take any angle, go around the circle to that angle, and then look at the coordinate to find the sine and the cosine. And then the tangent is just a slope. But how do we find this coordinate? Well, no matter where we are, we can draw a small right triangle to the y-axis. And then we can see right here, for example, that the cosine of star is adjacent over hypotenuse. The hypotenuse is still 1. This whole circle has a radius of 1. Can you see why the circle has a radius of 1? It has to do with the triangles that I drew in the first quadrant. Then the adjacent side is going to be the cosine of star. Since it's going out cosine of star, but now in the negative direction, this coordinate, cosine of bow tie, is going to be the negative of cosine of star. We can do the same thing for sine and use this to find the functions for any angle. I would pause the video here and try to find the sine of bow tie in terms of the sine of star in terms of the sine of bow tie. And one interesting thing is that this is on a circle now, what we call a unit circle. And a circle is mathematically defined as the set of points equidistant from the center. This means that this point is as far away from the center as this point is, and that point, and so on. This is basically the same thing as saying the radius of the circle is the same length wherever you look at it. And because of this, we can use the distance formula to say that the equation for this circle is x squared plus y squared equals the radius, or 1. Try to figure out why the distance formula helps you find the equation for a circle. We can see that based on our new formula, where x is the cosine of bow tie, and y is the sine of bow tie, that this suggests that the cosine of bow tie squared plus the sine of bow tie squared is 1. Is this true? Can you see how to show it based on our original triangles? Try this out. Meanwhile, I'm going to go look up recipes for pie. See you next time!